Last time, we used position and velocity to turn a second-order equation into arrows on a plane. Now we owe that move a proper explanation, and it may be the most useful minute in the series. Change comes in layers. Position says where you are. Velocity says how fast the position is changing. Acceleration says how fast the velocity is changing. A rate of a rate.
Is there a rate of acceleration?
There is. Drivers feel it as the lurch when someone stomps the brake, and engineers call it jerk. The ladder goes up as far as you like. Now look at where our spring's rule points. It does not hand you a slope for the position. It reaches 2 rungs up the ladder and dictates the acceleration. Pull the mass out, and it accelerates back towards center in proportion. That is what second order means here. The rule speaks from a higher rung. And it looks like trouble, because everything we are about to build wants to nudge each number along using its own rate, 1 rung at a time. Here is the move. Treat velocity as a variable in its own right, with its own seat at the table. The moment you do, the 1 second-order sentence splits into 2 first-order sentences. The position changes at a rate given by the velocity. The velocity changes at a rate given by the rule, minus the stiffness over the mass times the position. Nothing was added and nothing was lost. The same physics, rewritten as 2 coupled rules, each one plain first order. And now the picture from the first episode stops being a convenience and becomes inevitable. The state of the system is the pair, position, and velocity, 1 point in the phase plane. The first rule pushes that point sideways. The second rule pushes it up or down. Put the 2 pushes together, and they assemble exactly the arrow we drew at every point of the plane.
So the phase plane arrows were the 2 first-order equations all along.
They were. We had been using the move since the first episode. Now it has a name. And the move does not stop at second order. Suppose some rule reached 3 rungs up and dictated the jerk. Then keep 3 numbers. The position changes at the velocity. The velocity changes at the acceleration. The acceleration changes at whatever the rule says. 3 numbers, 3 plain first-order rules, and a state that is now a point in 3 dimensions. However high the ladder goes, the recipe is the same. An equation of order n becomes n numbers, and n first-order rules, 1 rung feeding the next. Think of that list of numbers as the system's memory, everything it must carry about its past to decide its future. A falling stone remembers exactly 2 things, where it is and how fast it is moving. Nothing else about its history matters. That little list is all the system needs to carry forward. And it is the state a computer updates. Which brings us to the payoff. Every solver we are about to meet speaks a single language. Hand me your state, it says, and I will ask the rules for every rate at once and nudge every number at once. Watch one nudge of the spring. The position moves a little, using the velocity. The velocity moves a little, using the rule. One step, both numbers together, and the point glides along the arrow. The solver never meets a second derivative. By the time the equation reaches it, there are no higher orders left, only a state and its rates. So here is where we stand. Any ordinary differential equation of any order now looks the same to a computer, a short list of numbers, and a rule for how fast each one changes. Which means a single recipe can simulate all of them, from a falling stone to a swinging pendulum to systems with thousands of moving parts. Next time we meet that recipe, take the arrow, take a small step, repeat.